Hello, welcome to Forest Learn. In this video, you can try a 1-mark question on induced EMF and electric fields. When you're done, we'll discuss the solution in detail so you can check your answer. Let's take a look at the question. A conducting rod of length L moves at speed v to the right, perpendicular to a uniform magnetic field of flux density B, directed into the screen. See diagram. As a result, free electrons move, causing the ends of the rod to become oppositely charged. When equilibrium is reached, no more charge accumulates at the ends. What is the magnitude and direction of the electric field strength when this happens? Please pause the video and have a go at this by yourself. And when you're done, unpause the video and we'll discuss the solution. Okay, welcome back. Before we discuss the solution, let me just say that as you follow the solution, it's a good idea to write down the main ideas and equations being discussed. This is a more active process than just passively listening and watching the solution, and will help you learn and retain the concepts better. So, as the rod moves to the right, so will the electrons in the atoms that make up the rod. And since the electrons are moving at right angles to the magnetic field lines directed into the screen, the electrons will experience a magnetic force. We can figure out the direction of this force from Fleming's left-hand rule. The first finger of our left hand should point into the screen, since that's the direction of the magnetic field. To figure out which way to point our second finger, we need to remember that current means conventional current. So, if electrons in the rod are moving right, the conventional current will be to the left. This is similar to how in an electric circuit, the electrons move in the opposite direction to the conventional current. Therefore, we must point our second finger to the left, and thus find that our thumb points down. You might find that you have to twist your elbow a little bit, and it might feel a bit uncomfortable, but make sure you can replicate this yourself. Let me also note here that you may be aware of Fleming's right-hand rule, but in my opinion, it's unnecessary and it overcomplicates matters. Everything you might want to answer in magnetism and electromagnetic induction can be answered with just Fleming's left-hand rule. There is no need for Fleming's right-hand rule. Given that we found that our left thumb points downwards, what this means is that the electrons in the rod will experience a magnetic force downwards. And in particular, the free electrons will be able to move downwards. So in this little picture here, you can see we've zoomed in onto a free electron, and there's a downwards magnetic force acting on it. And free electrons will accumulate, will move down towards the bottom of the rod, therefore making this bottom end negatively charged. And at the same time, the top of the rod will become positively charged due to the depletion of free electrons. The magnitude of this magnetic force, call it F subscript m, is given by the product of the flux density B with the charge of the particle Q multiplied by the speed at which the charged particle is moving V. And that's just the speed at which the rod itself is moving to the right. And given that we're dealing with an electron here, we can just replace Q with the magnitude of the electron charge, E. So let's add that to our diagram here. Now, once net charge has started accumulating at the ends of the rod, the free electrons are repelled by the negative charge at the bottom and attracted to the positive charge at the top. In other words, an electric field now exists inside the rod, and therefore there is an upward electrostatic force on the free electrons. This electrostatic force, call it F subscript E, is given by the magnitude of the charge, E, multiplied by the electric field strength, capital E. Let's add that to our diagram as well. As the question states, eventually equilibrium is reached, meaning the forces acting on a free electron must balance. So equating the forces, in other words equating the magnetic force to the electrostatic force, we find the following. If we cancel off the charge, little e, from both sides, we find that the magnitude of the electric field strength is equal to BV, the product of the flux density multiplied by the speed of the rod. And the question also asks for the direction of the electric field strength, and that's simply just downwards. Remember, the direction of electric field lines indicate the direction of the electrostatic force on a positive charge. That's it for the question. But notice that we didn't use the length of the rod, capital L. Remember that for a uniform electric field, the field strength, capital E, is given by the potential difference, capital V, that exists across a distance d. For us here, the potential difference exists across the length of the conducting rod. So d for us here is just L, the length of the rod. And if we rearrange for the potential difference, capital V, we get that that's equal to the field strength times L, and we can use our result for the field strength, E is equal to B times small v, and we end up with this. But capital V is basically the induced EMF. So we've proven the formula for induced EMF for when a conductor moves or cuts through a magnetic field at right angles. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and leave a comment. I'd love to hear from you. Thank you for listening, and I hope to see you soon.